Don't forget to subscribe and ring that bell.
Hey, 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 we are going to continue the 2013 AP Calculus AB practice exam put out by College Board. All right. We are going to finish section 1, part A. That is the final multiple choice problems, 21 through 28. And we don't get a calculator. You know what? We don't need no stinking calculator because we're smart enough to do this on our own. Let's begin. You know what? The previous two videos, problems 1 through 20, I guess 1 through 10 and 11 through 20, they were some complicated problems. But you know what? We're starting 21 with a graph, and I love me some graphs. So 21 reads, the graph of function f is shown above. What is the value of the integral from 0 to 7 of f of x dx? All right, couple of things I just want to remind you about. Integration just means area under the curve, especially if I have no equation in a graph. I'm just taking the area under the curve. These are straight lines, so we can make some rectangles and triangles, which is what I like to do. Some people like to do the trapezoid in there. I don't really care as long as you get the right answer. But one thing I want to point out, there is total distance. That means everything is positive, every area you come up with, okay? And then there's displacement. Okay, that means when I have a graph, only the things above the x-axis should be considered a positive value, and any area that's below the x-axis should be considered negative. All right, look what they give us. An integral is displacement. So anything below the x-axis, this particularly right here, we should consider a negative value when we calculate it. Everything above the x-axis, okay, is considered a positive value when we combine them. If they wanted us to do total distance, the problem would say maybe this is the speed of a car, what's the total distance the car goes? Or if they give us an integral, the integral would have the absolute values in it, okay? So that would be total distance. There are no absolute value bars in the integral for problem 21. So we're not doing this. We're doing displacement here. Let's find our areas. Again, I like triangles. Okay, we have a triangle on the bottom here. I'm going to create a triangle here, rectangle here. And you know what? I'm going to do a rectangle and a triangle. That's just how I roll, kids. So let's do this. We got a width of 2 and a height of 1. So the area of this rectangle, 2 times 1, is 2. We got a base of 2, and this is a height of 1. My triangle is 1/2 base times height. 1/2 times 2 times 1. So that is going to be an area of 1. All right. We have a height of 2 and a width of 2. For my square, I guess, rectangle, four-sided figure. 2 times 2 is 4. And then we have 2 times 1 again. It's the same triangle. It's this same thing right here. 1/2 times 2 times 1. So that's going to be 1. All those numbers that are circled, my 2 plus my 1 plus my 4 plus my 1, those are all positive values. So I'm going to add them all together. I have 3, 7, that's 8. Okay? All of this up here is a positive 8. The triangle in red, 2, and that is a distance of 2. It is 1/2 my base times my height. So half of 4 is 2. But this is considered negative because it's below the x-axis. So if I combine that, 6. Bam. That is choice A, and we are off and going. It's a good start. It's a good problem to start with. All right, 22. The function f is continuous for all real numbers. Okay, it's continuous. That's nice. And the average rate of change, okay, that's the slope, okay, on the closed interval from 6 to 9. So that's the slope between 2 points. Okay, these 2 points here, when x is 6 to when x is 9, that's negative 3/2 is. So it equals negative 3/2. So for some c value between 6 and 9, there is no value for c such that the derivative is negative 3/2, of which, or of the following, which must be true. This is screaming mean value theorem knowledge. My average slope, which is my change in y over my change in x, which is basically y2 minus y1 over x2 minus x1, okay, has to equal the derivative at some point, and they actually use c in a lot of, has to equal the derivative at some point. This is an x value. They're just putting some c in there. This has to be true, okay? If my function is differentiable everywhere, which means it also has to be continuous everywhere. If these two things are true about my graph, then this has to be true, which means this thing in the box is true, okay? Now, they tell us it's continuous. That's this right here. But then they say that, okay, the average rate of change is negative 3/2. But then they say there is no value. So they're saying this cannot be negative 3/2. So if it's continuous, but the mean value theorem isn't true, that means it can't be differentiable. Okay, it can't be differentiable, because if it was continuous and it was differentiable, this would 110% be absolutely 100% true, but it's not based on what they tell us in the problem. So choice E, f is not differentiable on that interval from 6 to 9. 23. Let f be the function defined by f of x equals 2x plus e to the x. If g of x is the inverse of f of x for all x, and the point 0, 1 is on the graph of f, find, or what is the value of g prime of 1? Okay, first of all, anytime I see a g, I'm going to change it to f inverse, okay? So let's take a look at this. They want me to find g prime, the derivative of g at 1. Well, g is the inverse of f, okay? So if they want to find the derivative of g, they want us to find the derivative of the inverse of f at 1. My derivatives for inverses are, let's go to the calligraphy pen, 1 over the derivative of the inverse at the value of x, which happens to be 1. We write it just like we say it. It's 1 over the derivative of the inverse. Okay? Now, the problem is, I need to find, and the toughest part, and I say toughest, really it's not toughest, the part we don't do the most often, I should say, is finding the inverse of f at 1. Once I do that, I can find the derivative. That's easy. I mean, that's what calculus is about. That's what we always do. But I need to find this first. So let's go to our problem and see, okay, this x and y, this coordinate is on the graph of f, not the inverse of f, but f. That means f of 0 is 1. Okay, that's on the graph of f. Let's keep in mind that when we deal with inverses, don't we just switch x's and y's? We do. That's the whole premise of inverses, which means this x will become the y. This y will become the x. So look what we have here. The inverse of f at 1 is 0. So the inverse of f at 1 is 0. That's what's going to go in there. So I have 1 over the derivative of f at 0. Now it's easy. Now it's stuff that we do all the time. I just got to find the derivative of f at 0. Hey, 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 if this is f, let's find the derivative. So the derivative of f is the derivative of 2x, well, that's just 2, plus the derivative of e to the x is e to the x. So let's plug a 0 in for that x. 2 plus e to the 0. Anything, and I mean anything, to the power of 0 is 1. No, it's not 0. Silly. 2 plus 1 is 3. That means this value is 3. 1 over 3. And that, my friends, is choice B. Number 24. The function g is given by g of x equals 4x cubed plus 3x squared minus 6x plus 1. What is the absolute minimum value of g on the closed interval from -2 to 1? Okay, I don't care about anything outside this. I just want when x is -2 to when x is 1, and I want to find the low points. Mins and maxes, bing, bing, bing. The bell should be going off because this is first derivative. Okay, and I want a negative slope or a negative first derivative, then a positive first derivative around a critical point. Okay, that's how I find a min value. Okay, that's how I find a minimum point. Okay, so how do I find a critical point? I take my first derivative and set it equal to 0. So let's start by taking the first derivative here. All right, so g prime of x is the derivative of 4x cubed. Well, that's 12x squared. The derivative of 3x squared, well, that's 6x minus the derivative of 6x, which is just 6. The derivative of 1, a constant, that's 0. So bye-bye. That goes bye-bye. All right. Well, now we got to set this equal to 0, which means it looks like, oh, Lord, we're going to have to factor. Factoring never goes away. So let's set this equal to 0. I'm going to divide both sides by 6. So I'm going to divide a 6 out of everything. So I end up with 2x squared plus x minus 1 equals 0. And if I factor this, I could do slip and slide, but I'm just going to do like a guess and check thing here. I should end up with 2x times x, and this has to be a 1 times 1 plus minus. There you go. If I FOIL that, if I do, well, I'm going to get a positive x, positive 1. Why do I think that should be a negative? That should be a positive. Okay, I'm good. I'm good. So let's now T-bone this and solve this. We'll go here, right. Set each one of these equal to 0. 2x minus 1 equals 0. X plus 1 equals 0. I add 1, then divide by 2. So x equals positive 1/2. And then I just subtract 1 from both sides. X is negative 1. I'm going to put that on a number line. How about that? How about that, huh? Okay. So actually on my number line, I have an interval here. Keep that in mind. I only go from -2 to 1. So it's going to stop here at -2, not go on forever. It's going to stop here at 1. And I have two values, -1 and positive 1/2. All right? And I know that my first derivative of g is equal to 0 at these 2 points. That we just solved out. Those are our x values in the bottom. So I need to check values in between. All right? Or left and right of my zeros. Okay? So I need to check anything that's in this interval, anything that's in this interval, and numbers that are in this interval to see if my g prime value is positive or negative. I don't care about the number. I just care about the sign. So let us begin. Let's pick one of the easier ones. Let's pick 0 right in the middle. If I throw a 0 into this version of my first derivative, 2 times 0 goes to 0. Bye-bye. 0, bye-bye. I really just have -1. So my answer would be -1. So this will be negative, which means it goes down like this, my graph. All right, let's pick, I don't know, let's use the number 1 here. That's to the right. That's in my right side. I'm going to plug that 1 into this version for x's. Okay, so I'd have 2 times 1 minus 1, and in the other parenthesis, it's 1 plus 1. Okay, so 2 minus 1 is a positive 1. 1 plus 1 is a positive 2. If I multiply those, I get a positive 2. I don't care about the 2. I just care that it's positive. Okay, so that means positive, 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 positive. Okay, it looks like there's a min right here. Let's check. -2. I'm going to put a -2 into the same set of parentheses for x. Okay, so I get 2 times -2 minus 1. That's -5 times -2 plus 1, which is -1. That gives me a positive 5. I don't care about the 5. I just care that it's positive, which means this is increasing, okay? So I've got this graph. It goes up, down, and up. Now, it looks like I have a minimum value right here. However, since I have endpoints, I got to check the endpoints to make sure that they are not lower than my minimum. The only endpoint I got to check is this. This is a low point. So these two black coordinates, these two black points, when x is 1/2 and when x is -2 right here, I got to see the y values. They don't want to know where the minimum occurs. They want to know the minimum value. Okay, I'm going to have a coordinate for my minimum. This is the location or where it occurs, the x. The actual value of my minimum is the y. All right, which means, oh God, I'm going to have to throw 1/2 into the original equation, and I'm going to have to throw a -2 into the original equation and see which one's actually lower, which one has a smaller y value. That's okay. We got this. So g of x is 4x cubed plus 3x squared minus 6x. Is that plus 1? Plus 1. So again, what we're doing here is we're going to see which value of g. Let's throw a -2 in first. Which location, -2 or 1/2, has a lower coordinate, a smaller y value. So I got 4 to -2 cubed. That's -8 times 4. It's -32. Plus 3 times -2 squared. That's 4 times 3. That's 12. Minus 6 times -2. That's also positive 12. Plus 1. All right, well, we got -20, -8, -7. So the coordinate, when x is -2, my y is -7. This is the min value when x is -2. We have to do the same thing at 1/2 x. Okay, so g of 1/2. 4 times 1/2 cubed. That's 1/8 times 4, which is 4/8, which is really a half. Plus, okay, 3 times 1/2 squared. Okay, that's 3 times 1/4. That's 3/4. Okay. Minus 6 times 1/2, which is, what is that? -3. Half of 6 is 3. Plus 1. Now, look, I'm not sure exactly what this is going to be. I mean, I can do it out. Dang it. This is the same thing as saying 2/4, right? 1/2. So I got 5/4. Oh, man, I'm running out of space here. I have 5/4, which is the same as 1 1/4, minus 3 plus 1. So 1 1/4 plus 1 is 2 1/4 minus 3, which is -3/4. So when x is 1/2, y is negative 3/4. Okay, which y value? Negative 3/4 or negative 7 is smaller? Negative 7 is much further down on the y-axis than negative 3/4. That's a lot of work. There's a lot of algebra to do. So my answer, the minimum value is negative 7. It happens at the endpoint where x is negative 2, but the value, the y value is negative 7. Okay, these problems are starting to step it up here. 25. Which of the following is a solution to the differential equation dy dx equals ey plus x? Oh, man. With the initial condition y of 0 equals a negative ln of 4. Don't fret, because this is supposed to be easier. We're able to do this without a calculator, so don't freak out. I'm going to have to separate. See, all my answers are y equals. I need to get an equation y equals out of my derivative, which I'm going to have to integrate. But I'm going to do this with separable differential equations. I'm going to get my y and dy on one side. I'm going to get my x and dx on the other. The issue is, how do you separate that exponent? Whenever you add exponents, okay, that means you multiply common bases together. What do I mean? If I have x squared times x to the 5th, that's like saying x to the 2 plus 5, which is x to the 7th. We currently have this. We're going to break it up to here. Okay, so if I have these as e's, e to the 2 plus 5, that's like e to the 2 times e to the 5. But guess what? We don't have 2 and 5. We have y and x, so it's like e to the y times e to the x. So this is going to be e to the y times e to the x equals dy dx. All right, all right, all right, all right. So what we're going to have to do here is the following. Okay. We're going to multiply the left side times dx. Bye-bye. I multiply the left side times dx. I divide the right side by e to the y. Or if you want, instead of dividing, I can multiply by 1 over e to the y. Okay? This is going to cancel with this. And what I do to the right side, I have to do to the left. So let's rewrite what we have. On the left side, we have 1 over e to the y dy. Okay? Equals e to the x dx. And I'm going to rewrite the left side. Before I do anything, I mean, I'm going to have to integrate both sides. I get that. But let me change this and bring this up and negate the exponent. It will make that a lot easier. So I'm integrating e to the negative y dy. And that's going to equal the integration of e to the x dx. Okay, now it's going to get much simpler because these integrations are easy peasy. All right, this one right here is going to end up being negative e to the negative y. But don't forget, plus a constant. There are no bounds. It's going to equal the integration of e to the x is e to the x plus a constant. These constants are different. So I'm going to call this constant 1 and constant 2. All right? Maybe they're the same, but maybe not. Okay? So I'm just going to call them constant 1 and constant 2. So the first thing I'm going to do is I'm going to get my constants on one side. All right? So let's subtract constant 1 from both sides. Boom. Negative e to the negative y equals e to the x. When I have a constant and I subtract a constant, it just ends up being a constant, my friends. Don't get crazy. All right? Now, here's the lovely part. I have this equation right here. What do they give me? What initial condition do they give me? Because I need to solve for c at this point. Okay? And I could solve for c if it was the only unknown. And right now I have an x and a y and a c. I just want to solve for the c. So I need values for my x and y. I'm going to go up here. All right. This is a function. When x is 0, my output y is negative ln of 4. So I actually have this coordinate. And those are the values I'm going to use for my x and y. All right. So let's go back down here. At x 0, y is negative ln of 4. Okay. So let's plug those in for my x and y. Negative e to the negative y, which is negative ln of 4, equals e to the x, which is 0, plus c. Okay. Okay, this is doable. How come? First of all, whenever I subtract a negative in this exponent, I get a positive. So I've got negative e to the ln of 4 equals e to the 0 is just 1 plus c. All right. And at this point, you guys should know that e and ln sort of, they kind of get rid of each other. What do I mean? These cancel. I'm just left with negative 4 equals 1 plus c. Well, let's subtract 1. Negative 5 equals c. Okay? But I'm not done. They want the equation. Okay? They want the equation. All right. So let's go back to our equation. Let's go back to this thing right here. And let's throw our negative 5 in for c. So we've got negative e to the negative y equals e to the x. Well, this was plus c, but c is a negative 5. So this is what we have right here. And we want to get it the y alone. So I'm naturally going to apply an ln to both sides to get rid of my e's. But before I do that, why don't we just, let's divide both sides by negative 1. So I've got e to the negative y equals the negation of e to the x plus 5. So I'm just flipping both the signs. Now let's take the natural log of both sides. This cancels. I have negative y equals the natural log of negative e to the x plus 5. All right, that's nothing too crazy. And now, again, let's just multiply or divide by negative 1. So I've got y equals the negation of natural log of negative e to the x plus 5. That was some work like the last problem. A lot of, I mean, not easy work, but it's not complicated. You need to know your rules with natural log and e. Okay? Integrating e to the x is simple. Well, let's see what we got here. I think I see an answer. Yeah, stupid dad joke. The answer is choice C. Negative ln time of negative e to the x plus 5. 26. If you understand your relationships between integrals and derivatives, how they apply to the original equation, this one's cake. Meaning, which of the following is the antiderivative of this? Okay, antiderivative is integration. All right, so if I have an equation here, and I have the derivative of it, okay, this way is the derivative, obviously, but going backward is the integration. So basically, if I integrate the derivative of something, it gives me the original equation. No? Yes, it does. So which one of these is the antiderivative? All right? That means if I take the antiderivative integration of this, and I'm going backward from this, that means this is the derivative of some original equation. Which one of these could be the original equation? If I look at it that way, because to integrate that would be tough, okay? But if I look at it that way, that means this right here has to be the derivative of one of these, A, B, C, D, and E. So I think it's easier to just take the derivative of each one of those and figure out which one, when I take the derivative of any of these, Okay, one of those derivatives should give you this. That's going to be a million times easier to do it that way. Okay, I hope my explanation didn't freak you out here, but really, I should leave that there. I'll just erase this. All right, so we have the derivative. Okay, when we integrate it, we get the original equation. Okay, so let's take the derivative of the original equation and find this. And right off the bat, one of these things jumps out. Isn't this the same thing as this, except the t and the x are switched? So what happens if I take the derivative of an integral? Oh, my friends, we got this. Okay, what happens if I take the derivative of this? Is it going to equal what they gave me? Well, let's find out. Okay, derivatives and integrations cancel, and that dummy variable goes bye-bye. And my upper bound, which is an x, just goes in for the t. Eureka, they match. The derivative of e is this, which means the integration of this, going backwards, is this. Okay, no other option, A, B, C, or D, if you take the derivative of it, will give you square root of 1 plus x cubed. Two more problems left, 27 and 28, and let's begin 27. For time t is greater than or equal to 0, the height of an object suspended from a spring is given by h of t, which equals 16 plus 7 cosine of pi t over 4. What is the average height of the object from t equals 0 to t equals 2? All right, here's what has to jump out to you if you don't get this. The average height. Height is not a rate. That is just a value, which means we're really just finding the average value. Okay, and the average value is when I integrate a function. In this case, it's h of t from some bounds, a to b. But if it's the average value, I need to multiply that times 1 over the difference of those bounds. That is the average value theorem. Earlier in this problem, we did a mean value theorem. Okay, earlier in one of these problems, whatever, the answer was it wasn't differentiable. I don't know, 22, 23. But that's for derivatives, the mean value theorem. The average value theorem is for integrations. All right, so we're going to integrate this. Let's set up our integral. Okay, I'm going to integrate, of course, my h of t, which is 16 plus 7 cosine of pi t over 4 dt. All right, I want that from time 0 to time 2. So that means I got to multiply by the 1 over the difference of those bounds, 2 minus 0. All right, so let's just keep on trucking down here. All right, so this is going to be kind of a little bit of fun. Stick with it. We'll be good. All right, this is just going to be 1/2 out front. Okay, times. Okay, the integral. Let's do these. Let's break these up. It's like saying the integral from 0 to 2 of 16 dt plus the integral from 0 to 2 of 7 cosine of pi t over 4. Well, I can take that 7, that's a constant, and pull that out. So it's the cosine of pi t over 4 dt. There we go. This is going to be a little bit of work, but we'll do it slowly and very, very well organized. Boom, there we go. This is the easy one. If I integrate 16, it's just 16t, and I want that from 2 to 0. Okay, 1/2 is being multiplied times it all. Okay. All right. Plus 7. Oh, which would be, this would be nice. It was the integral of cosine of u. So I'm going to do u sub here. All right. I'm going to say that pi t over 4, that's going to be my u. Okay, which means my du is just going to be pi over 4 dt. All right, I only have a dt to sub in for, so I want to get this alone. So I'm going to multiply by 4 over pi. The 4's cancel, the pi's cancel, and what I do to one side, I have to do to the other. Okay, so in for dt is going to be du, but my 4 pi is a constant, so I'm going to put that on the outside as well. So let's go here. Let's get rid of this. And let's rewrite this. We have 7 times 4 over pi. All right? And my bounds are going to change. Okay, I've got to change my bounds. Okay, my upper bound was 2. Okay, so at t equals 2, I'm putting a 2 in here, 2 times pi over 4, which is really pi over 2. That's my new upper bound. My lower bound was 0. So if t equals 0, and I put a 0 in here, 0 times anything is still just 0. So that's my lower bound. All right, so let's integrate this. The integration of cosine of u is sine of u, and I want that from pi over 2 to 0. Okay, that's nice, that's fine. And again, if we're multiplying this, 7 times 4 is 28 over pi. Okay, so, oh my goodness, we still have a plus in front of this of 16t from 2 to 0. And oh, by the way, we're multiplying it times a half. Let's keep on trucking here. So let's move over here. So we have 1/2 times, let's do this one first. It's 16, and I'm going to put a 2 in, minus 16 times 0. Okay. I've got to add that. Oh, boy. I've got to add that. Oh, we're going to run out of space. To 28 over pi times the sine of pi over 2 minus the sine of 0. This all goes right here. Okay. All right. So let's do some more math. We got 1/2 on the outside. 32 minus 0. Okay. Plus 28 over pi times the sine of 90 is 1 minus the sine of 0 is 0. So really, I've got, oh my God, 1/2 times, if I subtract those, I just get 32 plus 28 over pi times 1 is 28 over pi. Ooh, man. I'm feeling like a mathematician now. All right, and if I multiply both of those by a half, which is the last step, half of 32 is 16, plus 28 pi, over pi times a half will just mean the 2 will be down here, okay? 2 is in a 28 14 times. My goodness, do we have an answer? 16 plus 14 over pi. That was remarkable. Let's just hope. Let's just hope that's an answer. Oh, thank God it's an answer. Okay, 16 plus 14 over pi. That was rigorous. Okay, kids? We say that problem had some rigor to it, had some depth, all without a calculator. That was a nasty problem to do without a calculator, but if you're patient and you go over it, you got it. They can't make anything easy, can they? Whoever wrote this 2013 practice exam should be, you know, I don't know, they should have rocks thrown at them when they're going to their car in the afternoon, leaving work. Just one rock. Let's not get crazy. We don't want to hurt anybody. Just scare them a little bit, you know. Just, it doesn't even have to hit them. Just, you know, whip it by them. 28. The function f is defined by f of x equals sine of x plus cosine of x for all x values between 0 and 2 pi inclusive. What is the x-coordinate of the point of inflection of the graph of f when it changes from concave down to concave up? Let's figure out what we're trying to find first, okay? I like this purple, okay? Point of inflection, that just means where the second derivative equals 0. And concavity changes around that. It either goes from plus to minus or minus to plus, all right? This is telling me I want the point of inflection where the graph changes from concave down to concave up. That's a negative second derivative to a positive. So I want it to be this, not this, okay? So I'm going to go from kind of like a sad face to a happy face. Right here at that point of inflection, that's where the second derivative equals 0, okay? And it goes from a negative second derivative to a positive. First things first, I need to find the second derivative of the equation they gave me, f of x. I got. So the first derivative, the derivative of sine, well, that's just cosine of x, plus the derivative of cosine is negative sine of x. So it's really cos of x minus sine of x. Okay. First derivative. The second derivative is the derivative of this. The derivative of cosine is negative sine of x minus the derivative of sine of x, which is cosine of x. Let's figure out where that's equal to 0. All right? Well, let's make it even easier for ourselves. Do you mind if I divide both sides by -1? That would be fantastic. Okay? So, I'm going to divide both sides by a -1. So I'm going to flip both these signs. So I've got sine of x plus cosine of x equals 0 still. Now, the only way this can happen, okay, the only way this can happen is if the sine of x and the cosine of x are the same value with different signs. What do I mean? If this value was, I'm making this up now, 3, wouldn't this value also have to be 3 but negative? And vice versa. If this one was -3, wouldn't this one have to be a 3 but positive in order to equal 0 when I combine them? They would, friends. You must know your basic details and information about trigonometry. The only time sine and cosine are the same is when it is of 45 degrees. However, oh man, unit circle time. Let's do it in a different color. You know, red just, it's getting me working. It's getting my blood boiling. Okay, unit circle time. There you go. 45 degrees is right about here. Okay, the cosine is 1 over radical 2. And the sine is 1 over radical 2. All right? But here's the thing. If I combine those, they're the same sign, okay? That's going to be 2 over radical 2. I don't want that, okay? I want them to be different. I want one to be positive and one to be negative. So in the first quadrant, all of them are positive. In the second quadrant, sine is positive, but cosine and tangent are negative. In the third quadrant, tangent is positive, but sine and cosine are both negative. And in the fourth quadrant, cosine is positive, and sine and tangent are both negative. Okay, so in the first quadrant, all 3 of them are positive. So let's look where they're different. Okay, here we already know this isn't going to work. They're both the same sign. We don't want that. Okay? Ooh, but in this quadrant, sine is positive and cosine is negative, so that can work. In this quadrant here, all right, in the third quadrant, they're both negative to the same side. And in this quadrant here, okay, cosine and sine are negative. So I'm going to have to consider 45-degree angle here and a 45-degree angle here. All right? If this is 90 and this is 180, that means this is 135 degrees. Okay? And I got to consider kind of this 45-degree angle here, which means if I go all the way around, okay, this is 360, and I go back 45, this is 315 degrees. So these are the two angles that will make this, okay, that will make that work, where I'll have my second derivative equal to 0, okay? Because in the second quadrant, my sine is a positive 1 over radical 2, and my cosine is a negative 1 over radical 2. If I combine them, I get my 0. And in the fourth quadrant, my cosine is the positive 1 over radical 2, and my sine is the negative 1 over radical 2. If I combine those, I will get 0 again. However, both of those aren't my answer. Remember, it needs to go from a negative value to positive of my second derivative. My God. Here we go. Let's get a number line working here, kids. All right. In fact, it only goes from 0 to 2 pi. So here's 0. Here's 2 pi. We have 135 degrees. And we have 315 degrees. Okay? If you need to, you should probably, this is 3 pi over 4. So it's 2 pi minus pi over 4. Oh, my God. Oh, so it's 2 pi minus pi over 4, which is going to be, oh, my God, over 4. That's going to be 8 pi over 4, which will be 7 pi over 4. This is 7 pi over 4 here. Okay, they want it in radians. That's what your answer is, so we should do it here. The second derivative is 0 for both of these values. So which one of these am I going to go from negative on the left to positive on the right? One of them, because remember, we got to go negative to positive. Let's just put some values in here. All right? Let's pick 0 to start. The sine of 0 is 0, and the cosine of 0 is 1. Okay? Let me say that one more time. If I put a 0 into these x's, I get 0 plus 1. That's a positive value. So it's positive here. All right? In fact, let me back that up. Ready? Da-da, 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 da-da. Keep on going, keep on going. All right. I can't use this because I factored out the negative 1. I've got to use this one as my second derivative. Okay, so let's redo that again. I'm going to put my 0 right here into this x. The sine of 0 is still 0. Okay, that's good here, 0. Minus the cosine of 0 is 1, but I got to subtract my 1. 0 minus 1 is negative 1. So these are negatives. Let's pick 180 degrees. That is smack dab in the middle here. 180, which is just pi. Okay? The sine of 180, okay, I'm using this again. The sine of 180 is 0. The cosine of 180 is negative 1. I don't know where that pops up from. So it's 0 minus a negative 1, which is 0 plus 1, which is a positive value. Okay, now let's try 2 pi, the last one. Let's try 2 pi. Okay, again, I'm going to go right back to this that I'm circling in blue. The negation, the sign of 2 pi is 0. So it's like negative 0 minus. The cosine of 2 pi is 1. So I get negative 1. So this is minus 2. So which one of these zeros do I go from negative to positive? At 135. I go from negative to positive. This number, I go from positive to negative. Okay, remember, I want to go from negative to positive. Negative to positive. That's 3 pi over 4, which is 135 degrees. And that, my friends, was a lot to do, but we're done with it. Thank God. That was a lot, man. That was some tough work. Those last few problems take a while to do. I will see you when we start the multiple choice section where we actually get to use a calculator, which would have been nice for some of these. These were challenging. I'll see you.
Don't forget to subscribe and ring that bell.